In this video, we're going to discuss CRA models for the associative property of multiplication. So the associative property, thinking associate. So if you associate with something, you're connected to that. Or if you have an associate, that's someone that you have some connection to. There's not necessarily any kind of physical movement. So again, this is where we have the grouping symbols where numbers are associated together. So the associative property is saying that we can multiply, if all we're doing is multiplying values, we can start with any of them first and we will get the same result of the same total. Okay. So I'm going to show two different models. This one, one of the models I'm going to show isn't quite as commonly used, but I'll still show it just so we have an example. But for this first one, how we're going to interpret the numbers inside our grouping symbols, inside our parentheses, is those are going to be our area models. Okay, so we're going to make area models here. And then our other multiplier is going to tell us how many area models we have. Okay, so in this first one, and I'm going to do groups as rows. So here we have 2 times 3. So again, I kind of have this entire left-hand side shown already, but this 2 times 3, 2 rows of 3, that would just be one of these area models. And then we're going to multiply that by 4, so I'm going to say I'm going to have 4 of those area models. So I have 4 area models that have 2 by 3, so 4 groups of 6 square units here in this area model. So I have a total of 24 square units. Okay. So this is the left-hand side, and I'm just going to reuse all of these just so the board doesn't get too cluttered, but also to highlight this idea that it's equal because we're not adding any of these square units to this total, and we're not taking any away. So we're still going to use all 24 of these. Okay. So this is the 2 times 3 first in the parentheses, and then we're multiplying that by 4. So 4 groups of that area model. So over here, we're going to create these area models that have 3 rows with a size of 4. Okay, so I'll make one first. Okay, so there's one area model that has 3 rows of 4. So you can see how I'm just rearranging those original, that 4 groups of the 2 by 3 models. Okay, so now I have 2 groups of that 3 by 4 area model. And again, we can see that they're equal because all 24 of those square units stayed in our model. We didn't add anything to it, we didn't take anything away. Okay. And then, so that's one concrete model. I'm going to show one more that's not typically used outside of the context of volume. So we could call this a volume model. And obviously it's going to be a volume model because you have 3 multipliers. So that's kind of why it's not typically used, is because a lot of the operations when we're introducing these, we're just doing 2 multipliers or 2 add-ins or something. So, but I'll still show this one. So again, we're going to still, this 2 by 3, all right, we're going to think of that as area, but in this context of a volume model, we're going to think of that as the area of the base. So whatever multipliers are grouped, that's the area of the base, and we'll just do the groups as rows again. So 2 rows of 3, so that's the area of our base. And then that other multiplier, so whatever is outside the grouping symbol, is going to be the height. Or kind of in the context of volume, right? So this is the area of our base. The height, we can also think of that as multiple layers. Right? So this is one layer of 2 times 3, right? 2 groups of 3. We need 4 layers, so there's a second layer, and then there's a third layer, and then a fourth layer. Okay, so we can see, again, there'd be 24 cubes. Right, so on the left-hand side, this is how this is structured, as that the area of the base is 2 times 3, so 2 rows of 3. Okay, so how we can take this existing volume model and transition this to show that this is equal to the right-hand side of the equation. Again, I said inside the parentheses, that is going to be the area of the base. So we want 3 rows of 4. And we want 2 layers of that because that's that outside multiplier. Okay, so we don't even have to decompose this volume model. We don't have to rearrange it. All we have to do is turn it. Right, we just have to change what the base is. So thinking of a rectangular prism like this, right? Any of the faces could be the bases, since those opposite sides are always going to be congruent. So here we can see that we have 3 rows of 4, and we have 2 layers, right? So that's that second multiplier. And again, the reason that they're equal is because it's the same rectangular prism the entire time. We're just changing it from this face as our basis to this face as our basis. So we're not changing the total volume, since this is a volume model in this case. So that's showing that we're equal. Okay. For a representational model, that one's probably not going to be as commonly used, but I'll just do the drawing kind of the area models. And, right, so we want 2 rows of 3. So this is one group of 2 rows of 3, and we want 4. Okay, so there's a second one, third one, and then a fourth one. Okay, and then on the right hand side, right, we want area models. We have 3 rows of 4. Okay, so that's one group of 3 by 4, and we need 2 of those. These representational models will probably be a little bit less common, because then to kind of demonstrate and show that they're equal, right, we'd have to go through and count all of these. We couldn't start with this one and change it into this one necessarily without doing a bunch of crossing off and kind of moving around, but kind of in the same sense, this shows that both sides are equal. And then our abstract model is going to this actual equation, just using our actual grouping symbols, and just showing that both sides are equal because they have the exact same total, exact same number of objects in there.